All right, Math 150, Section 2, Lecture 12, Chain Rule. All right, so what I want to do today is I want to start with the one-dimensional chain rule. I want to really emphasize the common mistakes in using it. And I want to emphasize how you prove it. And then I want to go from that to proving the multivariable case. The notation is a mess. If you know linear algebra, you can make things a little bit better. We don't know linear algebra. I will show you enough so that you can use it and you can have a sense as to why it's true. And then if you take linear algebra, hopefully they will revisit it. All right, let's go to one dimension. So chain rule, one dimension. So let's let A of x be f of g of x. And the chain rule says A prime of x is f prime at g of x times g prime of x. And for those people who came in late, if you want to grab munchkins, I will put some over here. Okay. For those of you who didn't come in late, you're also welcome to grab munchkins. All right. There are two things to remember when you see the chain rule. The first is that we are evaluating f prime at the point g of x, not at the point x. The second is that we have a g prime of x over here. So what I want to do is I want to give a couple of examples to just really highlight what's going on. So for example, let's say f of x is the square root of x plus 2, and let's say g of x is x plus 3. In order for f of x to make sense, what must be true about my input x? So what do I need about my input x if I want this to make sense? What values of x will be fine? Yes? So if I put a -5, it's okay?
Oh, no. -2 or greater.
Okay, so x must be greater than or equal to -2. If I want to look at f of g of x, I would need g of x would come in over here, and I would need that to be greater than or equal to 2. So if I look at f of g of x, that's going to be the square root of g of x plus 2. And so I would need g of x to be greater than or equal to -2. So I would need x plus 3 to be greater than or equal to -2, which implies x is greater than or equal to -5. So as long as x is greater than or equal to -5, I can look at f of g of x. So if I take x equals -4, f of g of -4 is going to be the square root of g of -4 plus 2. And that's going to then be the square root of g of x is going to be x plus 3. So it's going to be -4 plus 3 plus 2. What is -4 plus 3 plus 2? 1. I have chosen this so that I should be able to do the calculation in my head. We get 1. Excellent. What if I had just done f of -4? What would happen if I just do f of -4? Then I have the square root of -4 plus 2. Oh, crap. Yeah. Right? We don't really work with the square roots of negative numbers in this class. What went wrong? Well, what went wrong is we evaluated f at the wrong place. We need f to have its input being at least -2. We got g of x was okay as long as x was greater than or equal to -5. So it would have been fine to evaluate g of x when x equals -4. And g of -4 turns out to just be -1. That's a perfectly fine input to feed into f. So this example is to really, really drive home the point that when we are evaluating these functions, we must be careful. If we start off by evaluating f at the point g of x, then f prime should be evaluated at g of x. They've got to be evaluated at the same place. Okay? That's one of the most common mistakes people make is they drop the g. Sometimes you'll be lucky and they'll make sense no matter what. If I take x equals 8, then f of 8 is okay, and I will get a reasonable answer out. This is actually a good situation. When you see the square root of -2, it means you made a massive mistake somewhere, and you know you did something wrong. If you try to put an f of negative, if you try to put an f of 8, you'll actually get a reasonable answer out, and you won't notice that you've made a mistake. So I really want you to be aware and watching where should we evaluate these. So that's the first thing, is to notice the g of x. The second thing I want you to notice is the g prime of x. So let's look at something a little bit similar. Let's look at f of x is x to the n. What's f prime of x? So what would f prime of x be? Yes?
Nx to the x.
Anything else? Times? Well, what's the one number I can put in here and make it without harming it? I can put in 1, right? How do I interpret that 1? It's really n x to the n minus 1 times x prime, times the derivative of x with respect to x. What is the derivative of x with respect to x? 1. So do we really want to keep writing 1 whenever we use the power rule? No. It's foolish. But if we now start having the chain rule, we have a of x is g of x to the n. Then we would get a prime of x is n g of x to the n minus 1 times g prime of x. This g prime of x is really just the 1. And you don't notice it when you look at just the power rule. It's there, but it's hard to see. When you write it like this, you can see where that g prime is coming from. Okay, so these are the two big mistakes in applying the chain rule. What I want to do now is I want to show you how to prove the chain rule in one dimension. And then after we do one dimension, we will do several dimensions. All right. So this is our setup. A of x is f of g of x. A prime of x is f prime g of x times g prime. All of the proofs of calculus results, all of the calculus rules, they start the same way. They start with the definition of the derivative. So we would know a prime of x is the limit as h goes to 0 of f of g of x plus h minus f of g of x divided by h. So this is just the definition of the derivative. All proofs start like this. What we would love is if the numerator was slightly different. We would love if this was f of g of x plus h. Move the h outside the argument of g. If we had that, then we would have f of g of x plus h minus f of g of x over h. That's just the derivative of f at what point? At g of x. It would be the derivative of f at g of x. Okay? So if we just had that, we would be fine. Unfortunately, we don't. But we have a lot of different definitions of the derivative. One definition of the derivative is the limit as h goes to 0. Another definition, we call, say, b prime of x naught is the limit as x goes to x naught of b of x minus b of x naught divided by x minus x naught. Just think of x as x naught plus h. So if you look at it like that, this is equivalent to the original standard definition of the derivative we look at. There's also the tangent line definition of the derivative, which we saw generalized nicely to multivariable. All right, so if we look at this now, this looks a lot like this. My point x naught is what? What does x naught look like in this framework? G of x. And my point x, terrible arrow. And my point x looks like what point? G of x plus h. So this is really looking like this. So what are the two things we can do by doing nothing? Or what are the two ways we can do nothing? We've got to raise hand. Add 0 or multiply by 1, right? So we have two different ways of doing nothing. Do you think we want to add 0 or do you think we want to multiply by 1 here? Yes. We want to multiply by 1. Why? What do we want to multiply by? Yeah, g of x plus h minus... Yeah, because if we multiply by that, this is looking a lot like the definition of the derivative. The numerator looks good, but the denominator is not quite right. So we multiply by 1, we can get the following, which is similar. And we'll get a prime of x is the limit as h goes to 0 of f of g of x plus h minus f of g of x divided by g of x plus h minus g of x times g of x plus h minus g of x over h. If you don't like this, it's going to get much worse. So enjoy it while you can. Of these two expressions, one of them I think is a little bit easier to see as h goes to 0. As h goes to 0, what does this quantity go to? It just goes to g prime x. This is our definition of the derivative of g at the point x. What does this quantity go to? Yes? F prime at the point g of x. And there's the chain rule. There is a small mistake in the argument I gave you. The book does it by doing like an approximation in the numerator and expanding things out. I like this approach because I think it really highlights where things come from. It really emphasizes where the g prime comes from. It keeps us close to the definition of the derivative, but there's a small technical mistake. I'll give you a couple of seconds. If anybody sees it, it is worth a full exemption on a homework assignment. Full credit for any homework assignment. So any thoughts as to what the mistake is? It can't hurt to guess if you want to try.
Wouldn't you? Never mind.
Okay.
I mean, because you would cancel those out, but that doesn't really change anything.
So it's a very small technical point you have to remember when we define the derivative. Okay, so how could we be getting 0 over 0? Good. So if g of x plus h minus g of x is 0 infinitely often, we would have 0 over 0. When we go to the definition of the derivative, we have the limit as h goes to 0 of, say, b of x plus h minus b of x over h. Oh, no, I'm sorry, we're doing x goes to x naught. X goes to x naught. So we have b of x minus b of x naught over x minus x naught. We are assuming that x does not equal x naught. If x equaled x naught, I'm not quite sure why it's going so high now, but if x equaled x naught, we would have 0 over 0. So when we take the limit, it's the limit as x gets closer and closer to x naught, but it's never x naught. Well, if we're taking the derivative, this is not really a big deal. But now that we have g of x plus h, it's possible that g of x plus h could equal g of x infinitely often. Consider g of x is x squared sine, I think, 1 over x. That will be 0 infinitely often near 0. I'm not quite sure why it's moving up higher and higher and higher, but all right. So we have this annoying situation where we could have 0 over 0. So there's two ways around this. One is to do a little bit more work, or the other is to say, I'm just going to assume I have a function that is not 0 infinitely often near a point. Most functions are not 0 infinitely often near a point. Again, I want to try to give you proofs and explanations that really highlight what's going on, and we can save for a real analysis class these hyper-technical situations. Somehow doing that adjusted the camera, interesting. Or we could say, well, what would it mean if we have these zeros infinitely often? Maybe the first derivative would have to be 0. And if the first derivative has to be 0, well, then we're going to get a 0 from this piece over here. So maybe everything will be okay. So I'm going to just avoid that case and not really deal with it. Okay? Any questions on the one-dimensional part? All right. Now it is time to do the n-dimensional case. I think this is the worst moment of the semester. Okay? But you only have to do it once. I have to do it twice today. You may want to write horizontally at some points today. All right, so what we want to do now is we want to do the multidimensional chain rule. So, in the interest of trying to minimize the confusion, I am going to look at the special case where we have a function of 3 variables, where those 3 variables themselves depend on 2 variables. I have no idea why it keeps going all the way up like this. Let's see if that does it. All right. So what we're going to do is we're going to start off with chain rule n dimensions. So in general, we're going to have x1 through xn depend on u1 through um. For us, what we'll do is we will do x, y, and z depend on u and w. The reason I'm not doing uv, it's not because I don't know my ABCs. I do know my alphabet. Why do you think I'm using uw instead of uv? U and V look very similar, and my handwriting sucks. Right? Let me choose two things that look significantly different, so it'll be a little bit easier to follow. Okay? So what this means is x is a function of u and w, y is a function of u and w, and z is a function of u and w. And I'll have g of uw will be x of uw, y of uw, and z of uw. Does g return a number, or does g return a vector? What does g return? A vector, right? It has 2 inputs, and it has 3 outputs. So what I want to do is I want you to clearly write down what's going on. So we start off with a point uv, and I'll write that that lives in R2. It's an element of R2. What does that mean? It means it's a pair of real numbers. R stands for real. I have a map G, which if you give it a uw, it will give us a xyz. And this lives where? This lives in R3. So we have a map G, which takes pairs of real numbers and gives us triples of real numbers. Okay? We now have a function f, which takes this triple and gives us a real number back. So I can write, I have a function f, which takes triples as inputs and returns a real number. If you want, think of your x, y, z as your position on the surface of the Earth. And maybe think of f as your temperature. And if you know your position on the Earth, you'll know your temperature. And maybe your position on the Earth depends on 2 variables, u and w. Maybe we'll assume the Earth is a perfect sphere, and so the radius is always constant. There are no mountains anymore. They've been eliminated. Purple Valley has been filled in. All that matters is your latitude and longitude. And so your x, y, z are now just a function of u and w. So I should be able to have a function that takes UW and directly gives me this real number. And it's a function that's going to basically mimic first going from UW to XYZ, and then going from XYZ here. What should we call that function? It has two names that are already on the board. So what would be the names of this function? Any thoughts? Yes?
G of f of w.
I'm sorry?
G of f of w.
Other way around. It's f of g. So the small circle means composition. You do the one on the inside first, and then the one on the outside second. So we first apply g, then we apply f. That's why I'm trying to draw arrows like this. And we've already named this function. Or no, we haven't. I have not named it yet. I'm sorry. It's slightly different than lecture 1. I will let a be the function f composed with g, which will map us directly from R2 to R. The way we compute a might be passing through this function f. We first take a UV pair, a UW pair, sorry, a UW pair, and then g gives us a triple. And now that we have a triple, we can use the function f and evaluate f at the triple. What some people do, which I do not like, is they will sometimes call f composed with g f. And they will abuse notation, they will overload notation, and they will use f and say, well, look, there's going to be no source of confusion. We now assume that we're on a perfect sphere and there's no radius, so I'm going to write f of theta phi to my spherical coordinates. And don't be confused. I don't like that notation. Yes?
F of g, why is it two-dimensional?
So g takes two pieces of input and gives us three pieces of output. F then takes three pieces of output and gives us one piece of input. So the net effect of f composed with g is we go from 2 dimensions to 3, and then from 3 to 1. So in order to compose, the input dimension of f must equal the output dimension of g. So f needs 3 pieces of information. Great, g gives me 3 pieces of information. So I will avoid, like the plague, overloading notation and calling f composed with gf. I don't like doing that. I will introduce another function g if necessary and just really drive home what's going on. All right, are we ready to get the proof over with? This will be several minutes. All right, so proof. The proof we're going to use is very similar to the tangent plane proof we did on Wednesday. It was not a coincidence to do it that way. We did the Manhattan approach, right? We went north-south, and then we went east-west. And we did this because we could add 0, and we could put in additional things and have a better sense of what's going on. All right. The more space you have horizontally, the better. Let's calculate the partial of a with respect to u. This is the limit as h goes to 0 of f of x of u plus h w, y of u plus h w, z of u plus h w, minus f of x of uw, y of uw, z of uw, divided by h. Okay? My function a is just f of g of, right? So remember, just a of ub is just f of g of ub. So just f of x of ub, y of ub, z of ub. And similarly, a of u plus h v would just be f of x of u plus h. Sorry, these are w's. I keep making this mistake. X of u plus hw, y of u plus hw, z of u plus hw. I'm just substituting those in. Everybody happy so far? Or at least willing to follow? We now have to add 0. All right? Let's try to think, what's a good 0 to add? we have x of u plus hw, u plus hw, u plus hw, uw, uw, uw. Wouldn't it have been wonderful if this was just y of uw and z of uw, so that the only thing that changed was the x component in the first? So what we're going to do is we're going to add an extra point. We're going to add x of uw, y of u plus hw, z of u plus hw, and subtract it. So if you want, we're starting off here with x of uw, y of uw, z of uw. And we want to end up with x of u plus h, w, y of u plus h, w, z of u plus h, w. And so the first thing we're going to do is we'll just come to this point here, which is x of uw, y of u plus hw, z of u plus hw. And so now the y and the z components of these two are the same, and it's only the x components that differ. Okay? All right. So is everybody somewhat clear on why this is a good choice of 0 to add? So now let's see what happens. So this is going to be... Where's this one? I need a lot of space. This is going to be the limit, as h goes to 0, of f of x of u plus h w, y of u plus h w, z of u plus h w, minus f of x of uw, y of u plus h w, z of u plus h w, divided by h, plus the limit as h goes to 0, really long line. So we subtract this, we have to add it back, x of u, w, y of u plus h, w, z of u plus h, w, minus f of x of uw, y of uw, z of uw, divided by h. All right. Now let's look at what's going on. The second component is the same in both of these. The third component is the same in both of these. What does this look like? What does this remind you of? Yes?
dA postulative dx.
The postulative of which with respect to x? Which function? Right. This looks like the partial derivative of f with respect to x. It's not exactly that because we have x of u plus h. If we had instead x of u plus h w, if it started off like that, so this would be the first component. It was like this: f of u comma w plus h. So just move the h out. So I'm just changing the x coordinate. Then that would look like the partial of f with respect to x. We don't quite have that. So what does this look like, which we already did earlier today? Yes? It looks like the one-dimensional chain rule. Everything else is the same. X is a function of two variables. This is my f of g of x. W is the same in both of them. It's like I'm just changing a little bit. All right. So let me move all the way down over here. And so let's look at what that piece would look like. So we will have the limit as h goes to 0 of f of x of u plus h w blah, blah, because the y and the z part aren't changing, minus f of u of xw, blah, blah, because it's the same, right? What do I divide by? I'm supposed to divide by h. I don't want to divide by h there. What should I divide instead by? Close, but not with an f. I want to do my chain rule. I should divide by x of u plus hw minus x of u plus minus x of uw. And I have to multiply that, so I'll have an x of u plus hw minus x of uw. Yes, did I make a mistake?
No, so on the top, it's f of u x. It's like, why is the u first?
Oh,
Okay.
I'm actually curious to go back to the video and see if I said it correctly and voted incorrectly. I have a colleague who once gave a lecture in English but voted in French because he was in Quebec.
Okay, cool.
And he did that in real time very, very well. Okay. Sorry about that. And then the two blahs are the same. So we have two expressions again. One of them is, I think, a little bit easier to recognize. We have the limit as h goes to 0 of x of u plus hw minus x of uw over h. This is the definition of what? D what? Partial x with respect to u. dx du. Right? We're holding the w component constant. We're changing the first component. That's the definition of dx du. And if you look over here, that's just the derivative of f with respect to u. Or sorry, with respect to x. With respect to x, because it's with respect to the first component of f. F is a function of 3 inputs. I'm changing the first input. This looks like the partial of f with respect to x. Now we have to be very careful and remember that we have to evaluate this at the point g of uv. That's where we evaluate this. Where do we evaluate partial x, partial u? We evaluate that at the point uw. We're 1/3 of the way there. You do not want to see the rest of the similar algebra, so this is where we will just wave our hands, right? We handled the first piece. We now have the second piece over here. We're going to add 0 exactly as before. We're going to multiply by 1 exactly as before, and that next piece will become a df dy dy du. And then we'll be left with one other piece. What do you think that piece is going to become? df dz dz du. Okay, and so when the dust settles, we get dA du at the point uw is equal to this plus df dy at the point g of uv, g of uw, sorry, times dy du at the point uw plus partial f partial z at the point g of uw times dz du at uw. And that is the chain rule. Okay? So this is in the special case where we have 3 inputs depending on 2 inputs. There are lots of other cases you can consider. So I will write down what the answer is in full generality. I'm not going to do the proof. The proof is very similar to this. It's just more notation. And you can see that what you want to do is you want to find a good way to write down. So how do we keep adding 0? How do we keep multiplying by 1? So let's say g of u1 through um is equal to x1 of u1 through um dot 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 xn of u1 through um. So g takes m inputs and gives us n outputs. we assume we have some function f which needs n inputs and returns a number. And then we can look at a function a, which will just be f composed with g, which will take m inputs and give us out one number. And what we would get is the derivative of a with respect to ui would be df dx1 at the point of g of u1 through um times dx1 dui at the point u1 through um plus yada 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 plus df dxn at the point g of u1 um times dxn dui u1 through um. All right, my hand is getting sore. You can begin to see now why people abuse notation. Even though it's a little confusing, it's annoying to keep writing all this stuff down. The more you write things down, the less likely you are to make a mistake. And so it's really worth taking the time and putting in the extra symbols. We're going to do a problem very soon, and I will just show you how to do the problem by just writing everything down. It's going to be a lot like U substitution. If you write U equals this, dV equals this, du equals this, v equals this, you have everything set up to now do your substitutions and not make a mistake. Let me just end with just a quick note before we do the example. Let's say I give you f of x, y, z equals 3x squared plus y squared minus z squared. What is partial f with respect to x? Yes?
6x.
6x. How many inputs do I need to evaluate this? df dx is a function of how many inputs?
1.
It looks like 1, but it's not a function of 1. How many inputs do I really need for df dx? 3. It's a function of 3 variables. If I gave you instead f of x, y, z equals 3x squared y to the 4th, z to the 8th, what's df dx? So we should now get 6x y to the 4th, z to the 8th. Is it clear here that this is a function of 3 variables? We should really be writing, whenever we do this, df dx at the point x, y, z, or at the point a, b, c, or at the point 3, 9, pi, whatever. By an abuse of notation, we often drop writing down that this is at the point x, y, z, just in the interest of space. Yes?
Notation question.
Mm-hmm.
What is G of U W represent? From
Oh, over here?
there.
Over here?
Yeah.
G of UW is going to be, it's going to be the triple x of UW, y of UW, z of UW. It's not triple. And remember, if f needs 3 inputs, f can't be a function of u and v. It's got to be, somehow I got to take u and v, and from that pair, I have to get a triple. G is how I do that. And so this is why for me, for the chain rule, I always want to be very clear. Here's my f, here's my g, here's my f composed with g. Okay. So going back to what we had over here, when you look at this, it's clear that this really needs 3 pieces of input. When you look at just 6x, you might be tempted to think it's a function of just one variable. It turns out it's a function of 3 variables where it doesn't care about y and z. Y and z have no effect on the value of df dx. But it is a function of 3 variables. And again, the most common mistakes in the chain rule are forgetting where to evaluate things. All right. Any questions about the theory? Let's do a problem. All right. So here is a really nice problem. I will consider 2 variables that are functions of 2 variables. I chose 3 variables and 2 variables for the first problem because I wanted to be clear the danger of evaluating things at the wrong point. That's why I spent time, making sure, is it being evaluated at the right spot? This is why I wanted to have 1 as a function of 3 and 1 as a function of 2. So if you tried to put it at the wrong spot, things would break down. Let's let x of r theta equal r cosine theta and y of r theta equal r sine theta. Okay, those functions should look familiar. Where have we seen these? Polar coordinates. Right? So I'm going to look at the function f of x of r, f of xy is going to be x squared plus 3y squared. And I'll let a of r theta be f of x of r theta, y r theta. So if you want, my g of r theta is just x of r theta, y of r theta. And I want to compute how a depends on theta. Well, by the chain rule, we know this is just partial f with respect to x at the point x of r theta, y of r theta, times dx d theta at the point r theta, plus df dy at the point x of r theta, y of r theta, times the point dy d theta at r and theta. And when you look at this, you might be tempted to say, oh, I want to just cancel this dx with that dx and that dy. You can't quite cancel like that. But when you sum all of them, it does give you the derivative of the composition with respect to theta. If I had given you, I'll leave it like this. So we've got 4 things we need to compute. And this is how I like to compute them. The first is we need to compute the partial of f with respect to x. So what's df dx? df dx is just 2x. And then let's do df dx at the point x of r theta, y of r theta. Because that's what I'm going to have to substitute in. I'm not going to be substituting 2x. I'm going to be substituting something in terms of r and theta. So what would 2x be when I now say x equals r cosine theta and y equals r sine theta? What would df dx be? It would just be 2 r cosine theta. Right? Wherever you see an x, you just replace r cosine theta. Wherever you see a y, you replace r sine theta. Okay? We need to also compute dx d theta. So what's dx d theta? Bless you. What's dx d theta? So I look at r cosine theta, and I take the derivative of that with respect to theta. So what's the derivative of r cosine theta with respect to theta? I'm sorry? Not 2r. Negative r sine theta. And so just really being explicit, I'm evaluating the point r theta, it's negative r sine theta. Because when I take the partial of this with respect to theta, r is a constant. So when I take the derivative with respect to theta, r is just a constant. What's the derivative of cosine? The derivative of cosine is just negative sine. So the hard part is remembering is the derivative of cosine goes to sine and the derivative of sine goes to cosine, but one of them has a negative sign. How do you remember which one has the negative sign? So the way I like to remember it is the derivative of cosine is minus sine of theta is minus sine. So that's a way to remember where the minus sign is. Right? Any way that works for you is fine, but you've got to remember which one has the minus sign. If you're having trouble, you can just think of the picture. Here's my circle. This point is cosine theta, sine theta. As I increase the theta initially, is cosine going up or going down? Is cosine getting larger or smaller? Smaller. So since it's getting smaller, its derivative should be negative. So if you can't remember where's the negative sign, draw the picture. All right. 2 down, 2 to go. And I'm almost done, thank God. All right, df dy is what? 6y. So df dy at x r theta, y r theta is going to be 6 r sine theta. And then we have dy d theta is going to be r cosine theta. So, again, just writing it very explicitly, dy d theta at the point r theta is just going to be r cosine theta. Notice that we have every single piece we need to use the chain rule. We need df dx at this point times dx d theta at this point plus df dy at this point times dy d theta at this point. All we have to do is plug everything in, and we're done. And so when we plug everything in, we get dA d theta at the point r theta is equal to the following. So df dx at the right point will become 2r cosine theta, and then we multiply by minus r sine theta. Then we add df dy, which is 6r sine theta, and then we multiply by dy d theta, which is r cosine theta. Minus 2r squared cosine theta sine squared plus 6r squared cosine theta sine theta. So when the dust settles, it's 4r squared cosine theta sine theta. And that's the answer. Okay? This is how you would solve the problem using the chain rule. There's a faster way to solve this problem. Who is your favorite New England transcendentalist author? Thoreau. Okay? Why do we like Thoreau so much? What advice, what wisdom does he have? Simplify, simplify. We are trying to calculate dA d theta. A of r theta is just x, which is just r cosine theta squared plus 3 r sine of theta squared. So it's just r squared cosine squared theta plus 3 r squared sine squared theta. Is there a need to use the chain rule? Is there a need? No. You can use the chain rule if you want, but if I just write a explicitly as a function of r and theta, if I just substitute, and if I want to know what's dA d theta, let me just take the derivative directly. And if I just take the derivative directly, I get dA d theta. All right, so derivative of r squared, so I get r squared. Then the derivative of cosine squared is going to be 2 cosine theta negative sine theta, okay, plus 3 times r squared, and the derivative of sine squared will be 2 sine theta cosine theta. Ah, look, first piece, second piece. And when the dust settles, you're going to get 4r squared cosine theta sine theta. Yes?
Is that the case for all functions?
Whenever you could explicitly write down one in terms of the others, absolutely. So there will be a lot of times when it will be easier not to use the chain rule and just substitute in and then just take the derivatives directly. Sometimes it'll be easier to use the chain rule. On an exam, I might tell you, use the chain rule to compute this. And you'll go, but I could do it directly. Why do you think I would want you to do it directly, to use the chain rule? I want to make sure you know how to use the chain rule. But I will often choose a problem that you could do directly so you can check and see, did you get it right? So if you know what the answer is, you can say, oh, did I make a mistake somewhere? All right, so this was the low point of the semester. We've made it through it. Grab more munchkins. Enjoy the weather. Have a great weekend.